Okay, I'm going to talk about the statistical analysis that we did in connection to asthma. That was a long-term project that we carried with the Department of Health in Florida. The project was motivated from a social perspective at one point, and also from a scientific perspective, because the School of Science where I belong to is pretty interested in getting into system biophysics. And asthma is one of the emergent diseases or emerging conditions that involve a lot of different subsystems inside the human body. And a lot of people might be impacted by the result of this project. And one of the ideas is just to translate that into medical applications. Okay. So I distributed the presentation into the motivations that I just mentioned a little bit, the statistical analysis using mathematical packages, and then we're going to go through some kind of biophysical applications and how we can use Mathematica in order to address all these points. Okay, there is a fact in meteorology, exactly in biometeorology, that there cold fronts coming from the north of the United States when they move south, in different moments of the year, they produce episodes of outbreak of asthma at emergency departments. So typically in the northern side of the United States, in the period of August, September, they're producing high peak at emergency department, and sometimes people are calling that the school epidemic peak. But then the same peak is moving south, and by the time of January and February, so that peak of emergency department visit due to asthma are reaching South Florida. There is some kind of time series of the number of emergency department visits in some of the states of the United States, but there is not an overall surveillance problem. There's not any overall surveillance program collecting that kind of information for two reasons. One of the reasons, Steve just mentioned it yesterday in the keynote speaker dinner, it's pretty hard to get access to the health data. So to convince hospital or Department of Health to release that kind of data is not very easy in all states. Specifically in the state of Florida, they started to run a surveillance program for the last 8 years. And I was fortunate to work with the Florida Asthma Coalition and a BRACE project, and they were very gentle to provide the data that we use for that project. Okay, so mainly I will focus on three of the counties that belong to the southeast of Florida: Miami-Dade, Broward, and Palm Beach. They are ranking like the third, fourth, and fifth county with the number of asthma cases reported at the emergency department. Most of the cases of asthma are reported in the central part of Florida and in the north center part of Florida. There is some kind of microclimatic conditions first that apparently are favoring that number. And second, there is a lot of social cultural issues related with the disease. And that third category of social cultural events is pretty important because Florida Asthma Coalition has put forward a program of asthma management, make school free of asthma. And when people are just getting trained on how to manage asthma, the number of recurrent visits to the hospital has dropped significantly. So that's some of the things. As you can see from all these three graphs, there's a time series of a number of emergency department visits over time. The time unit here are taken as the day after January 1st, 2005. So that's the reason why you see, 365 correspond to the end of the first year, and so on. So we made it a relative unit because it's easy to be processed with time series analysis. Okay, if we look at the one in particular, Miami-Dade County, we did the smoothing and we tried different, I would say, strategies using moving averages. We use quantile regression. We use nonlinear feeding. We tested 3 different software in order to look for consistency for sensitivity. We did it with Mathematica. We did it with Origin. That's a software which is pretty common, and we did it with R. So we tested that thing with 3. And all 3 software, they were very consistent in telling us that there is a periodic signal imposed on a very, very slow quadratic background. So when you do the decomposition of the time series. We look at the mean number of cases per day for every year with the standard deviations, and we plotted that data in a standard unit, in C variables. And when you plot it in C variable, you can see that the number of cases are going beyond the first standard deviation, making that a very significant event, not just in the margin of the error. Okay, later on, we're looking at there's a seasonality, the weather conditions supposed to be involved in that. We use a Mathematica to get access to the weather information from the time series, the data time from all the airports around the South Florida. We got all that information, and then we did the correlation analysis between the number of emergency visits and a particular unit that we found the correlation with the largest value. To our surprise, even so that the graph are there, they look pretty similar. Now, when you do the correlation, linear correlation, you will see that the coefficient of variation for those are no higher than 14% when you do individual correlation. For example, the minimum temperature, and when you looked at the mean temperature for the day, so the largest value for the variation that you can get is 17% of variability, which is a surprising event because the graph look pretty similar. And then we look at the lagging effect, how many days in advance, so how many days people are getting exposed before they go into a consultation. And then we saw that even if you use the minimum value of the temperature, the variability that you can explain with a single weather event is no more than 24%. So that if you use a linear correlation analysis. So now you can go to a multilinear correlation also, and the result that you will get are not much better than the one that you get with the linear one. Now, if you do a Poisson analysis, which is pretty common in those cases because this is an interval, you have the average over the interval, then you can look at the odd in favor and the odd against, and then you can estimate how many cases can be changed if you change the weather conditions. And then you get a much better picture, and you get a more sensitivity to the weather condition. But that increase in the sensitivity, if you use a Poisson regression, it's going to be a little bit much better than that, but you never will see their correlation coefficient of the order of 70% or 80% capable to explain the variability of that. We tested the same thing with the humidity, the diurnal change of humidity, and then we look at actually at the combined parameter that is called the net effective temperature, which is a kind of a wind chill effect, but it involves now humidity, it involves the speed of the wind simultaneously, and it's the real temperature people are feeling. It's a physiological temperature that you feel. So when you look at the picture, you can see that the pattern for the net effective temperature pretty much reproduce that drop in temperature coincide with the peak in the emergency rooms, department visit. So, but if you do the correlation analysis, you will see that that correlation analysis about the 17% variability also, very similar that when you do that with the regular minimum temperature, which is telling you that the weather is not the direct cause of the impact of the number of cases of asthma at the emergency room. However, the weather might be an indirect comorbid factor. And we were exploring that before than anything else. So we look at the speed of the wind, and then we look at also at the environmental condition. We look at the number of, so the counting of ozone, ground ozone in Miami. And the data is showing that the ozone concentration is below the standards required by the EPA. Actually, if you try to do a cumulative effect of ozone over time, you will see that the correlation that you have in the increase in the number of cases is extremely small. So ozone in Florida doesn't play any role. Ozone played a role in the northeast of the United States for Boston and all the area of Massachusetts, that part over there, which high concentration of ozone, ground ozone, it might play a role. But for Florida, it doesn't play a role. And it might be understood pretty easy if you look at the windrows, which is the polar plot that you do for the speed of the wind and the strength of the wind. So how strong is the wind and in what direction the wind is blowing. Most of the time, the state of Florida, since it is a very narrow peninsula and the wind is very strong, so either the wind is taking any kind of pollution into the Lake Okeechobee or outside into both of either the Gulf of Mexico or into the Atlantic water. So pollution is not a problem for the state of Florida. So it takes me to the point that weather conditions is still in there, but in which way the weather conditions are affecting the number of people over there. Okay, then we look at the physics. And physics is the main point of that. And what part of physics? Thermal physics. So you can cover your body when there is cold. You can just get everything with your clothing. However, the only system in your body that you cannot cover out of interaction with the environment is your respiratory system. So your respiratory system is completely exposed to the environment, and you are exchanging heat completely and continuously with the environment. So then you have heat dissipated during respiration. They're coming in two ways, convective heat and evaporative heat. That evaporation that you're losing during the process of respiration is extremely important, and it might produce, for example, that your upper respiratory tract might lose humidity, and that humid layer that usually is located in the upper respiratory tract protect your upper respiratory tract from bacteria or viruses to get into the epithelial cells. So once you're drying these out, so you're exposing your epithelial cell to viruses that might be hanging in the air. Okay, we're looking at that, and we computed how much thermal stress you might get depending on the month of the year. And you can see there that in the first month of the year, in January, February, and then you see that again, and from November to December, you can get the highest thermal stress on the upper respiratory tract. So now, weather is not a direct effect, but it's producing thermal stress. And now you're talking about relation of stress and response from the body to that stress. Now, when you have a respiratory tract under stress, first, there's two things that happen. Your immunity usually drops, and second, the channels for viruses to get into your body are opening more easily. So if you explore that possibility, you will see that even on the daily basis, if you go to the stress on the daily basis, you will see that most of the time, by the end of every period, you got most of the negative thermal stress, which means as a stress due to cold, at the end of the year here in the area of South Florida, which means you got a lot of losses and a lot of dry out in the upper respiratory tract. It took me, or the group of people who worked on that project, to think that's supposed to be a relationship between the temperature, so the weather, and then like influenza or any kind of viruses that usually are present during the winter time in many areas of the United States. There are syncytial viruses, there are influenza viruses, and there's another group of family of viruses that are very present. Some people will show that like in a symptomatic way. Some people might show that in very direct symptomatic way. And the very dry air, which is very common during the months of winter, are very proactive for mold, bacteria, and viruses to get into your upper respiratory tract. So, which take me to analyze the problem of asthma based on a very known model that is called SIR model in epidemics, susceptible, infected, and recovered individual. Thinking about the asthma, in that case in South Florida at least, is epidemic triggered. So it means all those respiratory tract infections might be the triggering mechanism for them. But if you solve the SIR model, which is a model that includes a constant rate of transmission from susceptible to infected individual, so usually that is a constant. And then you're going to see that you got a peak in the epidemic, and then immediately that peak die out. However, if that constant is modified using a seasonally forced infection rate, and you solve that SRI model with the system of differential equation, so then you're going to see a completely different pattern. You will see now that you have periodic oscillations in the number of infected and recovered individuals. And if you add to that model a new compartment, including the exposed individuals that are asymptomatic, that might have a period for them to get sick, so then the number of oscillation and the chi-square testing with the experimental data, so the number of cases is much better in that case. So that is telling us that the support in favor of epidemic modeling is much better than things that we did it before. We then modify the model a little bit, and we introduce it explicitly the exposed individual, and then the exposed individual might have a probability Q that they might become infected, and they have a probability 1 minus Q that they are becoming asymptomatic, carrying the disease, but they're not showing sign. And with the time, they might show the sign, and they might become with a probability P infected direct individual, and then you go to the phase of recovery. We changed the system of differential equations, we solved the problem, and when you solve the problem, so you get a pretty, okay, if you consider the infection rate constant, that's the kind of solution you get. If you get the infection rate and the latency period with the variability of periodicity that we found in the time series, you get then a pretty good reproduction of the experimental result. That motivated us to look at the system part of the asthma as a combination of the immune and endocrine system in response to the thermal stress. We created the system graph for all the mediators from the cold, dry air to the air narrowing that might be involved. The system of differential equation that will result out of that is a pretty complicated one, and these are the modeling changes that we're expecting now. It's a system of nonlinear 16 equation with different time response, so you have a system that might respond pretty fast, system that might respond very slowly. And now you need to make compatible these two time windows. And this is one of the challenges that we are facing now with the modeling. And also, the last challenge that we are involved now, and I'm very thankful for this visit now, because I learned now how to get the matches for the upper respiratory tract here from Mathematica, and discretize that mesh so that I can solve the problem of fluid dynamics with thermal distribution. I have to solve those two things. But now I have the backbone from the upper respiratory tract, and I know already how to get the mesh to do that. So in conclusions, asthma is an emergent disease which is triggered indirectly by weather conditions. Weather conditions per se are not responsible for the episode of asthma. Weather conditions lead to evaporative losses. Then this might be a pretty good source for viruses to get into the system. And upper respiratory tract infections are the mechanism that seems to be the most important in South Florida. And the system biology approach that we're getting into now is more consistent with the 6 different phenotypes of asthma documented by the literature. Asthma is not a single, asthma is an emergent disease, which means it might come out from different pathways. And the reason for that, just telling that in mathematical terminology, your physiological description is a system with different metastable states. And now, depending from which metastable state you move on, or you move from, that's the phenotype of asthma that you will get. So that's the reason why you might get people that might get asthma from allergies, or you might get people that might get asthma just because they eat it too much one day. It's because it depends on the metastable state that you have there. And in order to explain that, you need to involve the endocrine system and the immune system, because endocrine is pretty easily related with the processes in your digestive system and your psychology, your mood system. And the mood immediately will also influence your immune system. So that's something that we call neuroendocrine immune interaction. So it's a three systems that are working together, and you cannot separate one from another. Saying that, I just want to acknowledge my institution for sponsoring this research, plus sponsoring the attendance to this conference, the Florida Asthma Coalition and the BRACE project for providing all the data and the networking, and three of my students who working in that project before with me. Janko Davila, he's a graduate BS in mathematics from our institution, and he's hired already by the University of Colorado in Boulder. Ashley Perez, she graduated as a BS in mathematics, and she now works for the Miami Public-Day School. And she's the last student that came from Miami-Dade College during the Summer Research Institute, and she did all the modeling about the epidemics. It's a biology major who learned mathematics in 1 month. And she did a great job. So which is telling, for me, it was a sanity check that biology student might learn computing, and they could do a pretty great job. That was the myth that biology students cannot learn math or learn computing. So she is a proof that it could be done. Thank you for your attention.